When a brain injury occurs, Cerebrolysin, a parenteral biological drug consisting of peptides and amino acids, is given to the patient by infusion. In this way, Cerebrolysin reaches its place of action, the targeted tissue in the brain, directly and in full concentration. The blood vessels of the brain supply our most important organ with oxygen, glucose and other nutrients and remove metabolic products and carbon dioxide. The endothelial cells of the blood vessel walls have a remarkable anatomical property. They form the blood-brain barrier. The most specific feature of this barrier are the tight junctions, closely connecting the endothelial cells, which are only permeable to some molecules, for example water or nutrients entering the brain. In contrast, large molecules, including many drugs, are held back by this structure. However, due to its molecular structure, Cerebrolysin is small enough to be able to pass the blood-brain barrier. This enables Cerebrolysin to act directly in the brain and its neuronal tissues. The final destination for Cerebrolysin is the neurovascular unit, which consists of blood vessels, microglia cells, astrocytes, pericytes, oligodendrocytes, and neurons with axons and dendrites, etc. In the neurovascular unit, Cerebrolysin interacts with all different components and areas, triggering specific activities to normalize brain functions. Learn more about the essential characteristics of the effects of Cerebrolysin in the following videos. The accumulation of risk factors like age, high blood pressure, diabetes, obesity, smoking, physical inactivity, to name just a few, are the main causes of stroke, particularly ischemic stroke. An ischemic stroke occurs when a blood vessel is blocked by clots which have developed slowly over time and consist of substances transported through the bloodstream. Fibrin fibers with their adhesive properties attach to the vessel walls and enable other components like erythrocytes, thrombocytes, leukocytes, lipids and proteins to form a thrombus. This thrombus is growing and can partly or completely block the flow of blood in a blood vessel. A blockage of clot formation upstream may prevent oxygen and nutrients from reaching the tissues in that area. This is called ischemia. Due to a downstream deficiency and undersupply of oxygen and nutrients, endothelial cells become procoagulant, prothrombotic, and inflammatory. In this phase, endothelial cells release pro-inflammatory cytokines. These cytokines will be transported downstream with a slower blood flow and infect other endothelial cells. These cells become inflammatory as well and extend this process further. With the continued increase of the inflammatory state, endothelial cells in the vessel wall swell and cause the gaps between these cells to widen. This inflammatory process leads to a decline in the cell-connecting tight junctions, which are responsible for maintaining the blood-brain barrier's integrity. Consequently, this reduction of tight junction leads to structural and functional damage of the blood-brain barrier, and due to cell swelling, the vessel walls become fragile and develop microbleeds. This brittleness of the vessel walls can cause a hemorrhagic transformation, resulting in intracerebral hemorrhage. In addition to the inflammatory effect of cytokines, an upstream blockage in the vessel results in a downstream fibrin deposition detaching from the clot that can activate the inflammatory and prothrombotic status of the vasculature as well. Therefore, fibrin fibers which have intrinsically toxic properties can aggravate this process. Now the patient suffers from acute brain ischemia and related brain inflammation. Cerebrolysin, an agent with neuroprotective and anti-inflammatory properties, has been infused intravenously, travels through the bloodstream and reaches its targeted tissue. There, Cerebrolysin interacts with the endothelial cells and reduces the release of pro-inflammatory cytokines. The endothelial toxic factory ceases to operate, the vessels return to a normal state. This is achieved by the ability of Cerebrolysin to promote vascular integrity by activating angiopoietin-1 and vascular endothelia growth factor. For endothelial cells less damaged, cerebrolysin increases the number of tight junctions and thereby increases the integrity of the blood-brain barrier and the tightness of the vessels, thus also reducing the risk of hemorrhagic transformation. Consequently, cerebrolysin protects not only the vascular system and subsequently the brain tissue, but also reverses vascular damage. A thrombus dissolves after a large vessel occlusion and releases larger and smaller fragments into the bloodstream. Such circulating fragments consist of fibrin, erythrocytes, thrombocytes, leukocytes, lipids, and proteins. On their journey through the vascular system, these fragments travel along increasingly narrowing vessels and finally block the very small vessels in the microvasculature. Because the capillaries are getting too small, smaller than the fragment of the thrombus itself, this particle eventually gets stuck and blocks that very small vessel. This causes, albeit to a smaller degree, once again an ischemic state. Such microclots dissolve with time by naturally produced components of the body like endogenous plasminogen and other immune components. However, due to pro-inflammatory properties of the mini-thrombus, cells attached to the clot release pro-inflammatory cytokines and swell, which causes a further closure of the capillary. The released cytokines and fibrin get in contact with other endothelial cells and trigger more inflammation reactions. These blockages of the capillaries by the clot and the subsequent swelling of the endothelial cells can be considered as mini-strokes. The resulting undersupply with oxygen and nutrients leads to atrophy and associated microbleeds. These result very often in disturbed cognitive functions, so-called small vessel diseases, which can later on trigger complications such as post-stroke cognitive impairment or post-stroke dementia. Cerebrolysin is indicated for the treatment of all forms of vascular cognitive impairments and consists of small molecules with anti-inflammatory properties. The arriving cerebrolysin molecules reduce inflammation and reverse swelling. Normal blood flow is restored and activated endothelial cells stop their cytokine release. The affected microvasculature returns to normal function. Cerebrolysin has a positive impact on inflammation in the vasculature and parenchyma and reduces microbleeds. This in turn has a scientific proven effect on long-term prevention of post-stroke consequences such as small vessel disease and post-stroke dementia. When a clot is formed in the capillary or a particle gets stuck due to the vessel's decreasing diameter, this leads to a reduced blood flow or a complete blockage of the vessel and causes an ischemic condition. Due to this undersupply, blood vessels and capillaries atrophy, causing the vessels to contract and dissolve. As a consequence of this ischemic state, neurons slow down their communication with other neurons, loosen the connections of their dendrites and axons to neighboring cells, and finally degrade, whereas other neurons lose their myelin sheath and are reduced in their functionality. Such a blood clot may dissolve naturally or due to administration of thrombolytic agents. To counteract the threat of neuronal death, glial cells begin to release neurotrophic factors such as BDNF, CTNF, or NGF. These neurotrophic factors play an important role in neuronal survival, and they initiate a natural recovery process of the neuronal network called neuroplasticity. One of the most important mechanisms of neuroplasticity is the formation of new connections with intact, adjacent nerve cells. In these cells, the axons and dendrites begin to sprout, the density of dendritic spines increases, and new synapses are built up. Nevertheless, a recovery process includes much more. It comprises an orchestrated interaction of angiogenesis, neurogenesis, neurite growth and remyelination, because only this interaction is conducive to spontaneous recovery. However, this natural and spontaneous neuroplasticity is very limited in time. The initiation and promotion of neuroplasticity, with its sprouting and synaptogenesis, is one of the most important properties of cerebrolysin. In reality, recovery processes such as neuroplasticity and the administration of cerebrolysin occur simultaneously. For a better understanding of the effect of cerebrolysin, we will demonstrate them sequentially. Cerebrolysin itself has neurotrophic factor-like properties. It stimulates neurons and glial cells to synthesize neurotrophic factors like BDNF. These neurotrophic factors activate the outgrowth of axons and dendrites and trigger the formation of new synapses. Further, cerebrolysin enhances neurogenesis and angiogenesis and stimulates remyelination. In this way, new neural networks are created to compensate the functions of lost neurons. A vessel occlusion may occur due to the formation of a thrombus or when embolic particles are deposited. The blood flow is dramatically reduced and causes an undersupply of oxygen and nutrients in the downstream area of the vasculature. This triggers an ischemic condition. This ischemia provokes a cascade of vascular and neurodegenerative processes that cause atrophy of blood vessels, whereby the vessels contract and dissolve. Neurons as well deteriorate their neuronal functions and communication pathways with neighboring nerve cells or die in the worst case. A consequence of neurodegenerative processes is the activation of natural recovery processes characterized by neuroprotection, neuroplasticity, and neurogenesis. After neuronal death, neurogenesis is induced by glial cells. Surviving neurons start to produce neurotrophic factors, in particular brain-derived neurotrophic factors. Later, the expression of BDNF mainly occurs in endothelial cells of the vessels. Stroke-mediated BDNF and other NTF expressions induce the recruitment of neuronal precursor cells from the subventricular zone into the ischemic stratum. On their way to the injured area, these derooted neuroblasts use blood vessels as a physical scaffold for their migration. Once in the injured area, these neuronal precursor cells differentiate into neurons and integrate with other nerve cells into a new neural network. However, this natural neurogenesis is slow and has a very limited time window. After infusion, cerebrolysin reaches the endangered area of the brain. Due to its neurotrophic factor-like activity, cerebrolysin promotes and amplifies natural restorative processes like neurogenesis and angiogenesis. Cerebrolysin stimulates neurons, glial cells, and endothelial cells to express neurotrophic factors. It catalyzes the conversion of pro-BDNF to active BDNF, and it mimics neurotrophic factor activities. Consequently, more neurotrophic factors are available to induce migration and differentiation of neuroblasts and the reformation of a neuronal network. Cerebrolysin can be seen as a multi-targeted agent that amplifies multiple processes of protection and neurovascular recovery. The whole process ends when a functional network is restored, which is the physiological basis for recovery and a successful rehabilitation therapy.